universe is a very dynamic place. Once thought to be static and unchanging, the cosmos roils with activity. Clusters of galaxies spin and twirl in a dance of unprecedented scale, and all of it occurring in an ever-expanding ballroom. But how do we know this? How do we know these galaxies are interacting in such a way? We know the stars and galaxies are moving because we can see their light compress and expand as they move through the heavens. A star or galaxy moving towards us has a spectrum that is shifted to the blue as compared with a stationary spectrum, and redshifted if the object is moving away. There are three ways light from celestial objects can be shifted, and the amount is usually denoted by a dimensionless number, z. The first way is known as Doppler shift and is due to the proper motions of the stars and galaxies relative to each other. For example, the Andromeda galaxy has a spectrum that is blue shifted because it is heading straight towards our galaxy. Doppler shifts are usually small with a value of z less than 1. The second way light can be shifted is called a gravitational shift, and it is usually caused by light leaving a luminous body that is near an object with a large mass, such as a black hole or a neutron star. The third way is the most interesting, cosmological redshift, and it is caused by the expanding universe. Photons leaving a distant galaxy are stretched by expanding spacetime, always towards the red, and the amount of shift is directly related to its distance from us. Astronomers know which of these three is in effect by the object being observed. A moving nearby star or galaxy will exhibit a shift due to the Doppler effect. A star or other luminous object near something with lots of mass will have its spectrum shifted due to gravity, while very distant galaxies will always have a redshift, and it will be due to universal expansion. So how can there be measured redshifts greater than the speed of light? It turns out that an object moving at the speed of light would have a measured redshift of about 1.4 and would lie 4,200 million parsecs away. Two galaxies moving relative to each other are bound by the laws of relativity, so 1.4 will be about the largest Doppler redshift that can be recorded, and the photons left that star or galaxy 4.6 billion years after the Big Bang. Any galaxy moving away from us with a z greater than 1.4 is moving away from us at faster than the speed of light. Paradoxically, the Hubble Space Telescope routinely measures galaxies with cosmological redshifts of 8 or more. How is this possible? While the laws of relativity do limit the speed of two or more galaxies moving in relation to one another, the expansion of spacetime is not bound by this limit. Relativity places no limits on the speed with which creation can expand. The farther a galaxy is from us, the faster it is traveling. No limits. The most distant galaxies measured so far are around z equal 8. The light left those galaxies when the universe was only 600 million years old. So how can we possibly see the light from these galaxies if they are traveling so fast? The answer is that the motion of a galaxy now has no effect whatsoever on the light it emitted billions of years ago. The photon that is traveling towards us has no knowledge of what the galaxy does after it leaves. It is affected only by the increasing amount of spacetime as it travels. At the moment photons are emitted from very distant galaxies, they are not traveling faster than light. But as the galaxy continues to recede, and it has picked up speed until its redshift is greater than 1.4, any photons would not be able to outrun the galaxy, and we would observe the galaxy freeze, then slowly fade away. Our current value of the Hubble constant says that for every megaparsec of distance between two galaxies, the implications for this are rather bleak.